There we go. Okay, I'm recording. So I was just starting to talk about what we're going to do today. I was just mentioning the intermediate value theorem and the squeeze theorem. These were two theorems I skipped over while we were studying chapter 2 because they're not immediately relevant, and I wanted to kind of maintain our focus on like what are limits and how do you solve limits using the notions of continuity and that sort of thing. But the intermediate value theorem is a really important theorem in calculus, and we are probably going to want to like talk about it or reference it later in the semester. And the squeeze theorem is one of what I call the extended techniques. Anybody play music? Anybody play an instrument like saxophone or trumpet or something?
I play the flute.
Yeah, so with any instrument like flute or clarinet or anything really, there are these things that musicians call extended techniques, which are like the sorts of techniques you can use to make sounds. Like on the flute, I bet you can sort of like tap the keys, and there's like this thing called overblowing, or you can like hum or sing through the while you're playing it.
We do right now for a piece for contest we're doing. We have to jet whistle, and so we whistle into the flute, and it comes out like a whistling sound out of the flute. That's
an extended technique, right? Mm-hmm. It's the sort of thing that you don't learn when you're like first learning the instrument, right? So it's like, and it's got a kind of rare application, right? Like how often do you need to jet whistle through a flute? Like maybe twice in your career, like it depends on who you are and what kind of music you play. But like my point about the squeeze theorem is like, of all the different strategies for solving limits, the squeeze theorem is like an extended technique. It's like it comes up occasionally, but like sometimes you need it. Sometimes like, well, you can only solve this limit if you use this thing called the squeeze theorem. And there will be an important limit that we are going to be looking at, which is going to come up. I've hinted at this before in chapter 3. It involves the sine function, and it's going to use the squeeze theorem. So here's my plan, folks. I thought we could talk about those two topics today, just to sort of play catch up, and then I will give you a good first lesson on 3.1 tomorrow. Does that sound good? All right. So let's see. The extended techniques analogy, by the way, works real well for derivatives as well. Later in this chapter 3, we'll get to like, here are the weird strategies for taking derivatives of bizarre functions. It's fun. Okay, so we will begin with the first thing, the intermediate value theorem. The intermediate value theorem says this: if a function f of x is continuous on an interval from a to b, and f of a is, say, for example, less than f of b, or greater, doesn't really matter, just not equal, then for any value, say v, or what is the word? Any value, v, between the f of a and f of b, there will exist or does exist an x value c, which is going to be between a and b, such that f of c equals v. All right, so let's read that again and parse what the heck it means. So first of all, one of the key assumptions here is that the function is continuous. That is very important. Okay. So let's say here's your A and here's your B. Okay. And we have a function that is continuous on that interval. So maybe it does something like that, for example. That's a nice continuous line, right? I can draw it without, there's no jumps, there's no holes, there's no asymptotes, vertical asymptotes, right? Nice and continuous. And we have 2 points on that line, A, f of A, and B, f of B. And if I carefully trace over to my y-axis over here, this would be the f of A height, and this would be the f of B height on the y-axis, right? Now I said f of A is less than f of B, but this works as if f of A is greater than f of B, as long as they're not equal to each other. That's the kind of the point here. As long as there's some space in between them. Okay. Here's what the intermediate value theorem is saying. If you take any value, the y value in between these two, let's take that for example, then there's guaranteed to be a point on the graph on this little interval between A and B, which is at that height. So that means you're guaranteed to have an x value C, where f of C equals V. And this is true no matter which V you pick. So there, I pick that V. If I take a different, if I take like a different x value, or sorry, y value over here, say that one, well, such a point is still guaranteed to exist. In that case, it would be that guy right there. Okay, this is sort of an obvious theorem. If you kind of step back and look at it, it's like, hey, if the line goes continuously from this point to this point, you have to pass through all of the values in between. It's like if you're going to get from point A to point B, you have to go through all of the points in between if you're moving continuously. Like if you can't, like if you're walking, you have to pass through all of the points in between because you walk continuously, don't you? You can't, your path is always continuous because you can't teleport and you can't suddenly blink out of existence, right? This isn't Dungeons and Dragons, right? In the real world, things move continuously. So that's basically all this says. Okay, it's a nice, it's a very like, it's a very intuitive theorem. One of the ways it can be applied is to say like, oh, there's guaranteed to be like a zero on a given interval. So let's take an example function. Let's take, for example, the function f of x equals x squared minus 2. Okay, if I evaluate like f of 1, I get negative 1. If I evaluate f of 2, I get positive 2. Okay. All right. Pay careful attention here to those outputs, right? Negative 1 and positive 2. Since 0 is between negative 1 and 2, we know that f of x, oh, hang on a second. Since f of x is continuous and 0 is between negative 1 and 2, we know that f of x must have an x-intercept where f of something equals 0, right? Between x equals 1 and x equals 2. And the intermediate value theorem is what guarantees this knowledge. Can't spell guarantees. Okay. You can sort of plot a couple of points on here, 1 comma f of 1 and 2 comma f of 2. One of them is below the x-axis, one of them is above the x-axis, and so but must pass through the x-axis on the way there, like somewhere in between. Okay. You can use this to come up with estimates for what this x-intercept actually equals. This x-intercept is technically an irrational number, so it can be very hard to get your hands on. But you can use a sort of like trial and error iterative sort of approach to like get closer and closer. And as long as you're still negative on one side and positive on the other side, you know that you still have like a left and right boundary. Like one of them is to the left and one of them is to the right. So you can kind of like squeeze in, which actually this is not directly related to the squeeze theorem, but it's kind of similar. You can use the intermediate value theorem to just say like, well, as long as I'm getting negative values here and positive values here, my x-intercept must be somewhere in between. And that is one possible way that you could program. You could write a program to do that in sort of a trial and error approach to give you like a very, if you run it repeatedly, you could have it give you like a very accurate approximation of that irrational number where it crosses the x-axis. So there's just kind of like a hypothetical sort of way to apply this theorem, this very basic kind of idea. So this is unlikely to show up in any assignments. You actually do have a couple of homework problems about it, but it's unlikely to show up in like an exercise set just now. I do want you to do the homework problems because it'll give you a chance to like kind of just think it over and like kind of get it through your head, you know? But then the main reason we have this is because we're going to use it later this semester in some proofs. Any questions about the intermediate value theorem? You guys want to like look at one of the problems in the textbook?
Yes, please.
I believe it's in 2.4. Am I remembering that right? Yeah, here it is. It's in 2.4. All right, here's an example. This is problem 150. In this exercise, we want to use the intermediate value theorem. So in this exercise, we define a function, h of x. Now this function is defined piecewise. Okay, it's got a certain rule that you use to define it when x is less than or equal to 2. And there's this other rule that you use to define it when x is greater than 2. And we're really only interested on the interval 0 to 4. Okay. Over the interval 0 to 4, there is no value of x such that h of x equals 10. Okay. Although h of 0 is less than 10 and h of 4 is greater than 10. Explain why this does not contradict the intermediate value theorem. Okay. So what this is saying is, hey, you've got h of 0. What is h of 0? Let's just double check. H of 0, 0 is less than or equal to 2, so we would use this rule. So you plug in 0, 3 times 0 squared minus 4. That's negative 4. Right? And then h of 4, Well, 4 is greater than 2, so we would use this rule. So we'd use 5 plus 4 times 4. 5 plus 16 is 21. So yeah, what it's saying is you got 0, -4 down here, and you've got 4, 21 up here. $10 is a y value that lies in between these. Here's 10. And so the graph, if it goes from here to here, it should pass through that red line somewhere, right? No matter how it goes. But only if it's continuous. So probably what's happening here is that this function is not continuous. It has like a jump of some kind, right? So let's examine if it has a jump. You can do that by asking, what is the limit as x approaches 2? 2 is the only place where there could possibly be a jump, right? Because this is a polynomial, so it's continuous everywhere it's defined, and so is this. So the only place we could have a jump is at that point where the two different definitions come together. All right, so you can ask, what is the limit from the left? And what is the limit from the right? Well, oh, sorry, this is called H. On the left side of 2, for numbers less than 2, we use this definition, 3x squared minus 4. So the limit of h of x as x approaches 2 from the left is going to be equal to the limit of 3x squared minus 4, which is 3 times 2 squared minus 4. I can just plug the 2 in because, of course, that function is continuous, right? So I'm using direct substitution. I have 12 minus 4. I have 8. What is the limit of this right here, of 2 from the right? Well, on the right-hand side, for x values bigger than 2, you use that rule. So this would be equal to the limit of that other function. 5 plus 4x. And so I do 5 plus 4 times 2, 5 plus 8. And I get 13. Aha, these are not equal. I have a jump discontinuity. It's called, right? So, so that's why it doesn't violate the intermediate value theorem. It's because the function is not continuous on the interval 0 to 4. That's the reason. So, oh shoot, sorry. So there's one example of a homework problem. We'll look at one more real quick. I believe, did I assign you guys 153? I've assigned 153 in the past. I think I assigned 153. This one. Does this look familiar?
Yes, you did.
I did. Okay, great. So I'll explain how you can approach this problem. This is a similar, this is a problem where we basically have two functions. We have, let's say, f of x equals 2 to the x, and g of x equals x cubed. We want to know, oh, actually, no, sorry. Let me back up. You could think of this as two functions, but I actually don't want to do that because the intermediate value theorem isn't about two functions, is it? That was a bad idea. The intermediate value theorem is about one function, right? It's all about one function. And I've just been and earlier I explained about like how sometimes like in particular you can use the intermediate value theorem to see if a function has an x-intercept, right? Because like if you find a negative output and a positive output and it's continuous, you know it's got to hit 0 if it goes from negative to positive or vice versa. All right, so that's what this is about. This is about whether a function has a 0. Now, it doesn't say that, though. What it says instead is determine whether this equation has a solution. So a solution to, here's the key insight here, a solution to an equation is the same as a 0 of a function. That's something that you may have been taught in pre-calculus. Does that sound familiar? This whole idea of solving equations goes hand in hand with finding zeros of functions. Okay, and the reason is because if you take an equation, you can always just subtract to move everything over to one side and get 0 on the other side. And so then anytime you're asking if there's a solution to an equation, it could always be rephrased as, if I define a function like equal to all the stuff that's over here, does this function have a 0? If so, the x value that makes it 0 is also a solution to the original equation, and vice versa. So solutions to equations are the same as zeros of functions, right? You have to make sure you're looking at the right function. So when I defined f of x and g of x at the beginning, that was the wrong approach. What I want to do is just combine them together and define one function. And then we want to see on each of these intervals, in order to check if it could have a 0 on that interval, what we can do is evaluate f at those numbers on the endpoints. So let's do that. So I'm going to pull up my calculator to help me out, of course. Let's get a new Desmos page. Because I have to define this as my function here, 2 to the x minus x cubed. There we go. There's a function, 2 to the power x minus x cubed. And now all I've got to do is plug in the endpoints of this interval, right? So 1.25 and 1.375. So what f of 1.25 looks to be about 0.43-ish. So that's positive, by the way. And then f of 1.375 looks like negative 0.0059, which is negative. So now, because we have one of them positive and the other one negative, and because this is continuous, it's two continuous functions added together. And so the result of adding two continuous functions together or subtracted, doesn't really matter if it's added or subtracted, is still going to be continuous. Because that's continuous and we have going from positive to negative, we can say the intermediate value theorem guarantees there's going to be an x-intercept or 0 or a solution to the equation on that interval. Can't spell the word guarantees again. And now it's, I don't know. Anyway, it's just going to be spelled wrong. That's fine. And then, so that's that interval. And then you can check the same thing on the other interval. Now, if the intermediate value theorem doesn't guarantee it, that doesn't necessarily mean there isn't an x-intercept, because say you get positive on both sides. It could be that your function is positive here and it's positive here. It could be that it goes like that and it doesn't, or like, it just sort of does some other thing and it never hits the x-axis. But that doesn't necessarily mean that there isn't an x-intercept. It could be that it does this. Maybe there's two x-intercepts on that interval, or maybe there's only one and it just sort of touches briefly and then comes back up. You know what I mean? So just because you don't get like a positive and a negative doesn't mean that it didn't hit zero somewhere in between. It might, but it's not guaranteed by the theorem. That's the main point. Okay, so I'm going to export this page, and then we'll talk a little bit about the squeeze theorem. My choice. 26th today. Yeah. All right. The squeeze theorem. This one is in section 2.3, I believe. Yeah. So the squeeze theorem. Oh, hang on. I might have moved on a little too fast. There's a question in the chat that I should answer. Let's pull up the previous page again. The theorem is saying, intermediate value theorem is saying that if the function is continuous and the y values on an interval, right? So like if you look at an interval of x values and look at the corresponding y values, if those y values, if one of them is positive and the other one is negative, then you can be guaranteed that it's going to touch the x-axis somewhere in between. So there's two conditions. It has to be continuous, and on the interval, it has to go between negative and positive, right? Then you can say, yep, it has to cross the x-axis. Because there's no other way to get from one side of the x-axis to the other side of the x-axis while being continuous. If you get from one side to the other side without crossing through, you would have had to jump or teleport or have a vertical asymptote, Like if you can't get from one side of from one room to another room without crossing through the door, right? Unless you are a wizard. But continuity means like you obey the rules of like you gotta go there. You can't like, yeah. Sorry, I'm having fun with the analogies here, but that makes sense.
A little bit, but so then what were you doing on the left side with the V to C, and because that's not crossing the x-axis though?
Correct.
Is it just two different definitions for the theorem?
No, the crossing the x-axis is like a specific application of it, right? So like in general, you can have an f of a and an f of b over here, right? F of a and f of b, and the value that you're looking for is somewhere in between. Right, the value that you're finding is in between them. Now, if one of these is negative and the other one's positive, then in particular, 0 is a value between any negative number and any positive number. So that's just a particular way that you can use the theorem. Does that make sense?
So it's just a scientific way of saying that there's more points in the graph in between the 2 points?
Well, I'm not sure what you mean. I'm not sure you're asking.
So V and C, right? So those are just two different points saying that it is continuous, correct?
Well, in this situation over here, the V's represent the Y values and the C's represent the X values, right? This function is continuous on the entire interval. So what that means is like it's continuous at every point on this interval here. The main idea here is that if you take a possible output between the leftmost point at A and the rightmost point at B, if you take a possible Y value that's in between those, the function is guaranteed to hit that Y value somewhere on the interval between A and B. And the place where it's hit is being labeled C.
Okay.
Okay. All right, let's see. So, okay, so let's take a look at this other theorem. The squeeze theorem is a technique for solving a limit. And it says this. It says, I'm not going to type this time. It says, if you have three functions, f of x, and g of x, and h of x, three functions. And if you have this inequality, f of x is less than or equal to g of x, which in turn is less than or equal to h of x. And if that is true on some interval around an x value, which we'll call a. Okay, so if we have that, and so first of all, what does that mean? That just means that here's our x value, a. We're going to have like three functions. There's a top one, a middle one, and a bottom one. Oops. I'm going to draw the picture the way I want it to be here, which is more or less like this. So the top one is F. Oh, sorry, no. Actually, the top one is H. Here, I got to put that in the right order. Top one's H. The middle one is G. And the bottom one is F. Okay. Now, what it's saying is that it's top, middle, bottom on some interval around A. Now, it doesn't matter if that inequality gets violated somewhere else, like this, for example. Say that bottom function f goes up and it ends up above the other functions later on. That doesn't matter because that's like far enough away that it doesn't matter. What we're going to be doing is looking at a limit at A anyway. So we're gonna be taking the limit at A. And so all that matters is that for some interval around that point where you're going to be taking the limit, that this inequality is satisfied. So we don't really care about what's going on over here or over there. Okay, so so then what it says is we have a second condition, and if the limit as x approaches a of the bottom function f of x is equal to the limit as x approaches a of the top function h of x. Okay, if those limits are actually equal, let's give that point a name. Let's say that point is called v. That's some value v. Again, I'm just using the letter v today for values. Okay, then what that would mean in my picture is that like here at x equals a, my bottom function and my top function are approaching the same number. So I'm going to adjust my bottom function so that it looks right. So it's going something like that. So the point is that they're both approaching the same value And that value is whatever is going on right here. That's the value, that's the y value, v, okay? Or maybe actually, usually we use the letter L for limits, so maybe I should use the letter L. I think that's what the textbook does. So the point here is that the middle function that's in between the f and the h, it gets squeezed, right? If f and h are both approaching the same limit, then the middle function must also be approaching that limit. And that's it. That's the squeeze theorem. So let's look at an example. Oops. Let's look at the limit as x approaches 0 of what is the example I want to do? Hang on. I think it's x squared times sine of x. There we go. This is a classic example. Oh no, sine of 1 over x. That's what I want to do. We could apply it to the other one too, but it's more interesting if we do sine of 1 over x. So why is this interesting? Because if you try apply properties of limits, here's what happens. If you try to say, let's do the limit as x approaches 0 of x squared times the limit as x approaches 0 of sine of 1 over x, right? If you try to just multiply the limits together, this first limit here exists and equals 0. This second limit does not exist. Dang. It fails. So the reason it fails is because of this. If you have a limit that doesn't exist, you can't apply the properties of limits. These properties of limits only apply, they're only valid if all the individual limits exist. Now you may be thinking, well, if it's times 0, isn't the answer going to be 0 no matter what? Anybody thinking that? Isn't anything times 0 going to be 0? So if one of the two things that you're multiplying together is 0, isn't the whole thing going to be 0? If you're thinking that, I must politely ask you to stop thinking that, because that's not how it works with limits. We already know that's not how it works with limits, because we have already encountered 0 over 0 situations. Okay, so warning. With limits, 0 times anything does not necessarily equal 0.
It's mostly based on the equation, right?
It depends. It depends a lot on like the function that you're looking at. Yeah. So an example of this is stuff like we've already seen. This is my sort of go-to example here. or sorry, -1, looks like 0 times 1/0, which does not exist, I guess. Or maybe it's infinity, right? We could say that. It sort of looks like 0 times infinity, but not equal to 0. This limit actually equals a half, right? So we've done that exact limit a couple of times. You can factor it, you can cancel it, you plug in a 1, and you get 1/2. 1/1 plus 1 is a half. So yeah, you can't just say that this is going to equal 0 based on the fact that it's 0 times something. Okay, but that doesn't mean it's not equal to 0. It just means that this strategy doesn't allow us to conclude that it's 0. What we can do instead here is use the squeeze theorem. So the way you apply the squeeze theorem to this is you say, well, what do I know about sine? One of the things I know about sine, and this is true for sine of anything, put whatever you want inside the sine function. One thing that's guaranteed about the sine function is that its output lies between -1 and 1. That's what sine does, right? Sine goes between -1 and 1. It doesn't ever go outside of that boundary. And that's regardless of what its input is. So even if its input is something wacky, like 1/x, it's still going to be between -1 and 1. It has to be, because it's y coordinates on the unit circle, and the unit circle is locked within that interval, -1 to 1. It never goes outside. So so that sine function is guaranteed to be there. So then what I can do is I can say, let's multiply all parts of this inequality by x squared. This is a valid thing to do. X squared is going to be a positive number as long as x isn't 0. And so we're going to get this. And you'll notice now that I've done that, the function we're asking for the limit of lies right in between these two other functions. So here we have inequality of functions with the function we're curious about in the middle. And below it, we have -x squared, and above it, we have +x squared. And so then we can say, well, let's examine the limit of the bottom one, and the limit of the top one as x approaches 0. Well, the limit of -x squared equals 0, and the limit of +x squared also equals 0. So then, by the squeeze theorem, the limit of the middle function, you'd say, is also 0. Right? So that proves that this limit does indeed equal 0. That was correct, but just not for the reason you might have expected. Not for this reason over here. It's not 0 times something equals 0. It's, it's a little different. It's a little more subtle than that. Okay. So that is our squeeze theorem. We'll be, maybe we want to spend a little more time on the squeeze theorem later. I think we will. Like I said, we're going to come back to it. So when we come back to it, we'll spend a little more time discussing it just to make sure it's all like it, makes sense. But it's another very intuitive thing. It's like, hey, you got a function, they're both coming into the same place. So anything in the middle has to also go to that place too, because it gets squeezed in there. Yeah, it's kind of like a back door. Here we go. All right, everybody. This has been a little catch-up review or catch-up day But like I said, tomorrow we will actually start section 3.1 in earnest. And then we'll be back on track. So have a lovely day. I'll see you then.